Tonight on The Sleepy Scientist, we're drifting gently through the vast cosmic ocean, where invisible currents shape the very fabric of existence itself. In the quiet depths of space, there flows a presence so subtle, so ethereal, that it remained hidden from human understanding for most of our species' contemplative journey. Among the stars, this is the realm of dark matter, that mysterious substance which, like whispers in the night, speaks to us only through its gentle gravitational embrace of the visible universe. As we float through this cosmic meditation, we find ourselves surrounded by a universe that is far more mysterious and wonderful than our ancestors could have ever imagined. In the quiet space of our current understanding, we have discovered that everything we can see, every star that twinkles in the peaceful night sky, every galaxy spinning in its slow cosmic dance, every planet orbiting in silent harmony, represents only a small fraction of what actually exists in our universe. The rest, the vast majority of cosmic matter, remains invisible to our eyes, detectable only through its subtle influence on the matter we can observe. Gently, we discover that this invisible presence permeates everything around us. It flows through our solar system like a gentle cosmic breeze, passes through our planet as softly as moonlight through gossamer clouds, and even drifts through our own bodies as we sleep, leaving no trace except for its gravitational whispers that help hold the cosmos together in its grand, eternal dance. In the quiet space of scientific contemplation, this mysterious substance has earned the name dark matter, not because it is ominous or frightening, but simply because it does not emit, absorb, or reflect light in any way that our instruments can detect. It is dark in the same way that a gentle evening breeze is invisible, present everywhere but revealing itself only through its subtle effects on the world around it. Tonight, as we embark on this peaceful journey of discovery, we will explore the gentle mysteries of dark matter with the same quiet wonder that astronomers have felt for generations as they have slowly pieced together this cosmic puzzle. We will drift through the history of its discovery, float among the theoretical possibilities of what it might be, and contemplate its profound role in shaping the universe we call home. Like whispers in the night, the story of dark matter begins with observations so subtle that they were almost overlooked, clues so gentle that they required the most careful and patient scientific minds to recognize their significance. In the early decades of the 20th century, astronomers began to notice that something was not quite as it seemed in the cosmic dance of galaxies and galaxy clusters. As our journey continues through this contemplative exploration, we will discover how dark matter has influenced every aspect of cosmic evolution, from the first moments after the Big Bang to the formation of the galaxies that serve as island homes for billions of stars. We will explore how this invisible presence has shaped the cosmic web that connects all matter in the universe, creating a vast network of filaments and nodes that serves as the scaffolding upon which all visible structure has been built. In the quiet space of modern astrophysics, scientists estimate that dark matter comprises approximately 27% of the universe, making it more than 5 times more abundant than the ordinary matter that makes up stars, planets, and all life as we know it. Yet despite its overwhelming presence, dark matter remains one of the most profound mysteries in all of science, a cosmic riddle that continues to inspire new generations of researchers to peer ever deeper into the fundamental nature of reality itself. Gently, we discover that the search for dark matter has led humanity to build some of the most sensitive instruments ever conceived, detectors buried deep beneath the Earth's surface, where they wait in perfect silence for the rare whisper of a dark matter particle interacting with ordinary matter. These underground laboratories serve as quiet sanctuaries, where scientists listen patiently for signals that might reveal the true nature of the invisible universe that surrounds us all. As we float through this peaceful exploration, we will also encounter the space-based observatories that map the distribution of dark matter across cosmic distances, using the subtle bending of light itself to reveal where these invisible concentrations reside. These missions, with names like Euclid and the future Roman Space Telescope, serve as humanity's gentle eyes in space, quietly gathering the photons that carry information about the universe's hidden structure. Let us drift into the profound realization that dark matter represents more than just a scientific mystery. It is a humbling reminder of how much we still have to learn about our cosmic home. In an age when human knowledge might seem vast and comprehensive, dark matter whispers to us that the universe still holds secrets, far grander than anything we have yet discovered. The contemplative beauty of dark matter lies not only in its mystery, but in the elegant way it reveals itself through the language of gravity and motion, like a master poet who communicates through subtle metaphor. Rather than direct statement, dark matter speaks to us through the orbital velocities of stars in galaxies, through the dynamics of galaxy clusters, and through the large-scale structure of the cosmic web itself. In the quiet space of our current understanding, we recognize that dark matter has been an essential ingredient in the cosmic recipe that has given rise to the rich tapestry of structure we observe in the universe today. Without its gentle gravitational influence, galaxies would never have formed, stars would never have ignited, and the conditions necessary for life would never have emerged from the primordial cosmic soup. As our journey continues, we will explore the intimate connection between dark matter and the possibility of life. Throughout the universe, we will contemplate how the invisible scaffolding of dark matter has influenced the formation of planetary systems, the distribution of heavy elements necessary for rocky worlds, and the long-term stability of the cosmic environments where life might take root and flourish. Gently, we discover that the study of dark matter has also led to profound insights about the nature of space and time themselves. The search for this invisible substance has pushed the boundaries of particle physics, inspiring theories about extra dimensions, supersymmetry, and exotic forms of matter that exist beyond our everyday experience. Tonight, as we drift through this cosmic meditation, we will approach these complex concepts with the gentle curiosity of explorers. Setting foot on a new continent, we will not rush toward conclusions or become anxious about the implications of what we discover. Instead, we will allow ourselves to be carried along by the natural flow of scientific understanding, following the quiet evidence wherever it might lead us. Like whispers in the night, the story of dark matter reminds us that the universe is far stranger and more wonderful than we ever dared imagine. It challenges us to expand our conception of reality itself, to acknowledge that the cosmos contains forms of matter and energy that transcend our direct sensory experience, while still playing fundamental roles in the cosmic story of which we are all a part. In the quiet space of this exploration, we will discover that dark matter research represents humanity at its most thoughtful and patient. The scientists who dedicate their careers to understanding this invisible presence demonstrate a profound form of faith, not religious faith, but the scientist's faith that the universe is knowable, that its mysteries can be unraveled through careful observation, creative theoretical thinking, and persistent experimental investigation. As we begin our peaceful journey into the realm of dark matter, we carry with us the accumulated wisdom of generations of astronomers and physicists who have contributed to our growing understanding of this cosmic mystery. From the early observers who first noticed anomalies in galactic rotation curves, to the modern researchers operating sophisticated particle detectors in underground laboratories, each generation has added its own gentle discoveries to the ever-growing tapestry of human knowledge. Now we float toward the first major milestone in our contemplative exploration, the historical discovery of dark matter itself. We will meet the pioneering scientists whose careful observations first hinted at the existence of this invisible presence, and we will follow the gradual process by which the astronomical community came to accept that the universe contains far more than meets the eye. In the gentle flow of scientific progress, we will see how individual discoveries built upon one another, creating a growing body of evidence that eventually painted a compelling picture of a universe dominated by invisible matter. We will witness the patient accumulation of data, the careful analysis of observations, and the gradual emergence of a new understanding that would fundamentally change humanity's conception of cosmic reality. As our journey continues through this peaceful exploration, we will always remember that dark matter, despite its name, represents not darkness in any frightening sense, but rather the beautiful mystery of a universe that continues to surprise and delight us with its hidden complexity. It is a reminder that we live in a cosmos far more rich and intricate than our everyday experience might suggest. A universe where invisible currents of matter flow like gentle rivers through the space between the stars. Let's drift into this cosmic story with open minds and peaceful hearts, ready to be amazed by the subtle beauty of a universe that reveals its secrets only to those who approach it with patience, curiosity, and wonder. In the quiet space of our exploration, we will discover that dark matter is not just a scientific puzzle to be solved, but a profound meditation on the nature of reality itself and humanity's place within the vast, mysterious cosmos we call home. As our journey continues deeper into the cosmic mystery, we find ourselves floating back through time to the early decades of the 20th century, when astronomers began to notice subtle anomalies in their observations that would eventually lead to one of the most profound discoveries in the history of science. In the quiet space of observatories around the world, patient researchers were making measurements that would slowly reveal the existence of an invisible universe hidden behind the familiar glow of stars and galaxies. The story begins, like whispers in the night, with a Swiss astronomer named Fritz Zwicky, who in 1933 was conducting a peaceful study of the Coma Galaxy cluster, working at the Mount Wilson Observatory, high above the lights of Los Angeles. Zwicky spent countless serene nights measuring the velocities of individual galaxies within this distant cosmic congregation. What he discovered through his careful observations would puzzle astronomers for generations to come. Gently, we discover that Zwicky's measurements revealed something entirely unexpected about the Coma cluster. The individual galaxies within this cosmic family were moving far too quickly for the cluster to remain gravitationally bound if it contained only the matter that could be seen through telescopes. According to the laws of gravity as understood at the time, these rapidly moving galaxies should have long since dispersed into the cosmic void, leaving behind only empty space where the cluster now resided. In the quiet space of his calculations, Zwicky realized that the cluster must contain far more matter than what was visible to produce the gravitational field necessary to hold these speedy galaxies in their cosmic dance. He estimated that the cluster required approximately 400 times more matter than could be accounted for by the light-emitting stars and gas clouds that telescopes could observe. This missing mass, as it came to be known, represented the first clear evidence for what we now call dark matter. Zwicky coined the term Dunkelmaterie, dark matter in German, to describe this invisible presence. However, his discovery was so far ahead of its time that it was largely ignored by the astronomical community. In an era when the universe seemed to be composed primarily of stars and gas, the idea that most cosmic matter might be invisible struck many scientists as too radical to accept without additional evidence. Let's drift into the patient decades that followed, during which astronomers gradually accumulated more evidence for this mysterious invisible matter. The story of dark matter's acceptance by the scientific community is a beautiful example of how scientific understanding evolves through the careful accumulation of evidence rather than sudden revelations. Each new observation added another gentle piece to a cosmic puzzle that would take many years to fully appreciate. As our journey continues, we encounter the work of Vera Rubin, whose name has become synonymous with dark matter research. Through her groundbreaking observations of galaxy rotation curves in the 1970s, working at the Carnegie Institution with her colleague Kent Ford Rubin, embarked on a systematic study of how stars orbit within spiral galaxies. Measurements that would provide some of the most compelling evidence yet discovered for the existence of dark matter. In the quiet space of their research, Rubin and Ford used a sensitive spectrograph to measure the velocities of stars at various distances from the centers of spiral galaxies. Their expectation, based on the laws of orbital mechanics that govern planetary motion in our solar system, was that stars farther from a galaxy's center should orbit more slowly than those closer in, just as the outer planets in our solar system take longer to complete their orbits around the Sun. Gently, we discover that what Rubin and Ford found contradicted these expectations in the most profound way. Instead of decreasing with distance from the galactic center, the orbital velocities of stars remained roughly constant, even at the very edges of the galaxies they studied. This observation, now known as the flat rotation curve problem, indicated that galaxies must contain vast amounts of invisible matter, extending far beyond the visible disk of stars. Like whispers in the night, these rotation curve measurements spoke of a hidden universe that had been present all along, but had remained undetected because it interacted with ordinary matter only through the gentle force of gravity. The mathematical implications were clear. To produce the observed flat rotation curves, galaxies must be embedded within massive halos of dark matter that extend to distances far greater than the visible galactic disk. Through her patient observations of dozens of galaxies, Vera Rubin demonstrated that the flat rotation curve phenomenon was not an isolated anomaly, but rather a universal property of spiral galaxies. Each galaxy she studied showed the same telltale signature of invisible matter, providing overwhelming evidence that dark matter was not just a curiosity, found in a few unusual systems, but rather a fundamental component of cosmic structure. In the quiet space of scientific recognition, Rubin's work gradually gained acceptance throughout the astronomical community. Her meticulous observations and careful analysis provided the kind of systematic evidence that scientists require to accept revolutionary new ideas about the nature of the universe. The flat rotation curves became one of the cornerstone pieces of evidence supporting the dark matter hypothesis. Now we float toward an understanding of how these early discoveries fit into the broader context of cosmic evolution. The realization that galaxies are embedded within massive dark matter halos had profound implications for theories of how these magnificent cosmic structures formed and evolved over billions of years of cosmic history. As our journey continues through this contemplative exploration, we begin to appreciate how the discovery of dark matter represents a perfect example of the scientific method at work. Rather than accepting the first unusual observation as definitive proof of something new, the scientific community demanded additional evidence from multiple independent sources. Only when this evidence accumulated over several decades did dark matter become widely accepted as a real component of the universe. Gently, we discover that the process of scientific discovery often follows this same patient pattern. Individual researchers make careful observations that hint at new phenomena, but it takes time for the broader community to recognize the significance of these discoveries. In the case of dark matter, nearly 40 years passed between Zwicky's initial observations and the general acceptance of invisible matter as a major component of cosmic structure. Let's drift into an appreciation of the profound humility that these discoveries demanded from the scientific community. The realization that the visible universe represents only a small fraction of cosmic reality challenged fundamental assumptions about the nature of matter and energy. Astronomers had to accept that their telescopes, no matter how powerful, could directly observe only a tiny portion of what actually exists in the cosmos. In the quiet space of this new understanding, researchers began to recognize that dark matter was not just an interesting footnote to cosmic structure, but rather the dominant component that had guided the formation of galaxies, galaxy clusters, and the large-scale cosmic web itself. The invisible universe was not merely present, but was actually the primary sculptor of cosmic architecture. Like whispers in the night, additional evidence for dark matter began to emerge from other areas of astronomical research. Studies of gravitational lensing, the bending of light by massive objects, provided independent confirmation that galaxy clusters contained far more matter than could be seen in visible light. The cosmic microwave background radiation, the afterglow of the Big Bang itself, carried subtle imprints that were consistent with a universe dominated by dark matter. As our journey continues deeper into this cosmic mystery, we encounter the work of countless other researchers who contributed to our growing understanding of dark matter's role in the universe. Computer simulations began to show how dark matter might have provided the gravitational scaffolding necessary for galaxy formation. Theoretical physicists proposed various candidates for what dark matter particles might actually be. Gently, we discover that the story of dark matter's discovery illustrates one of the most beautiful aspects of scientific research, the way that patient observation can reveal truths about nature that transcend our everyday experience. The astronomers who first detected evidence for dark matter were not looking for something exotic or mysterious, they were simply trying to understand how galaxies and galaxy clusters behave under the influence of gravity. In the quiet space of their research, these scientists demonstrated the profound power of the scientific method to reveal hidden aspects of reality. By carefully measuring the motions of stars and galaxies, by analyzing the distribution of matter in cosmic structures, and by comparing observations with theoretical predictions, they were able to infer the existence of a form of matter that had never been directly detected. Now we float toward an appreciation of how these discoveries changed humanity's perspective on our place in the cosmos. The realization that we live in a universe dominated by invisible matter had philosophical, as well as scientific implications. It reminded us that reality extends far beyond what our senses can directly perceive, and that the cosmos is far stranger and more wonderful than we had previously imagined. Let's drift into contemplation of the profound questions that these discoveries raised. If the universe is indeed dominated by invisible matter, what does this tell us about the fundamental nature of reality? How many other hidden aspects of the cosmos remain to be discovered? What new instruments and techniques will be needed to probe deeper into these cosmic mysteries? As our journey continues through this peaceful exploration, we begin to see how the discovery of dark matter opened up entirely new areas of scientific research. Particle physicists began to consider what kinds of exotic particles might comprise this invisible matter. Cosmologists started to explore how dark matter might have influenced the early evolution of the universe. Astronomers developed new techniques for mapping the distribution of dark matter across cosmic distances. In the quiet space of modern research, we find that the legacy of pioneering scientists like Fritz, Zwicky, and Vera Rubin continues to inspire new generations of researchers. Their patient, careful approach to astronomical observation serves as a model for how science advances, through the accumulation of evidence rather than through sudden breakthroughs or dramatic revelations. Gently, we discover that the story of dark matter's discovery also illustrates the importance of keeping an open mind when confronted with unexpected observations. The astronomers who first noticed anomalies in galactic rotation curves could have dismissed these observations as experimental errors or instrumental problems. Instead, they pursued these anomalies with scientific rigor, eventually uncovering one of the most significant discoveries in the history of cosmology. Like whispers in the night, the evidence for dark matter accumulated slowly, but inexorably, building a compelling case for the existence of invisible matter that could no longer be ignored by the scientific community. This gradual process of acceptance reflects the inherent conservatism of science, which demands extraordinary evidence for extraordinary claims but ultimately embraces new ideas when the weight of evidence becomes overwhelming. As our contemplative journey prepares to move forward, we carry with us a deep appreciation for the patient astronomers, whose careful observations first revealed the existence of dark matter. Their work reminds us that the most profound discoveries often come not from dramatic experiments or theoretical breakthroughs, but from the quiet, persistent effort to understand the subtle details of how the universe actually behaves. In the gentle flow of scientific progress, we see how individual discoveries build upon one another to create ever deeper understanding of cosmic reality. The detection of dark matter was not the work of a single scientist or a single observation, but rather the result of many researchers working over many decades to piece together a cosmic puzzle of unprecedented complexity and beauty. Now we float toward the realm of theoretical contemplation, where physicists and cosmologists have spent decades gently exploring the possible nature of dark matter itself. In the quiet space of mathematical equations and computational models, researchers have proposed a fascinating variety of candidates for what this invisible substance might actually be. Each theoretical possibility opens up new avenues of investigation and offers its own unique insights into the fundamental nature of reality. As our journey continues into this contemplative exploration of possibilities, we encounter the most widely discussed candidate for dark matter, weakly interacting massive particles, known affectionately by scientists as WIMPs. These hypothetical particles represent a beautiful solution to the dark matter puzzle, possessing just the right properties to account for the invisible matter. that permeates our universe while remaining undetected by conventional means. Gently, we discover that WIMPs, as their name suggests, would interact with ordinary matter only through the weak nuclear force and gravity. This makes them nearly impossible to detect directly, as they would pass through ordinary matter almost as if it weren't there. Yet their gravitational influence would be substantial enough to account for the missing mass that astronomers have observed in galaxies and galaxy clusters. In the quiet space of particle physics theory, WIMPs emerge naturally from models that extend our current understanding of fundamental particles and forces. Many of these theories, including supersymmetry, predict the existence of stable massive particles that would have been produced in abundance during the early moments of the universe's existence. If such particles exist, they would have survived to the present day and would now comprise the dark matter that shapes cosmic structure. Like whispers in the night, WIMPs will be constantly streaming through our solar system, our planet, and even our own bodies, carrying with them the secrets of the invisible universe. Occasionally, perhaps once every few years in a kilogram of ordinary matter, a WIMP might interact directly with an atomic nucleus, producing a tiny signal that sensitive detectors might be able to observe. Let's drift into contemplation of another fascinating dark matter candidate, the Axion. Named after a laundry detergent because it would clean up certain theoretical problems in particle physics, Axions represent one of the most elegant solutions to multiple mysteries in fundamental physics. These hypothetical particles would be extraordinarily light, perhaps trillions of times lighter than even electrons, yet they could be produced in such vast quantities that they would account for all of the universe's dark matter. As our journey continues through this peaceful exploration of possibilities, we encounter the beautiful theoretical framework that gives rise to axions. These particles were originally proposed to solve a puzzle in quantum chromodynamics, the theory that describes the strong nuclear force, but physicists soon realized that axions produced in the early universe could provide a natural explanation for dark matter. Gently, we discover that axions would interact with ordinary matter and electromagnetic fields in ways that are almost unimaginably subtle. They might occasionally convert into photons when passing through strong magnetic fields, or they might cause tiny oscillations in the fundamental constants of nature. These interactions are so weak that detecting axions requires some of the most sensitive instruments ever conceived by human ingenuity. In the quiet space of theoretical physics, axions represent a profound connection between the world of particle physics and cosmology. The same theoretical framework that attempts to understand the behavior of quarks and gluons within atomic nuclei also predicts the existence of particles that could comprise the dark matter scaffolding of the entire universe. This unity of physics across vastly different scales speaks to the elegant mathematical structure that underlies all of natural reality. Now we float toward another intriguing possibility, sterile neutrinos. These hypothetical particles are related to the familiar neutrinos that stream constantly from the Sun and other cosmic sources, but they would interact even more weakly with ordinary matter. While regular neutrinos can interact through the weak nuclear force, sterile neutrinos would communicate with the rest of the universe only through gravity, and possibly through their mixing with ordinary neutrinos. Like whispers in the night, sterile neutrinos offer a particularly elegant solution to the dark matter mystery, because they would arise naturally from extensions to the standard model of particle physics that physicists have already proposed. For other reasons, these theories suggest that for every type of ordinary neutrino, there should exist a corresponding sterile neutrino with a much larger mass. As our journey continues through this contemplative exploration, we encounter the possibility that dark matter might not consist of a single type of particle, but rather an entire dark sector of physics that parallels our familiar world of electromagnetic interactions. Just as ordinary matter can form atoms, molecules, and complex structures through electromagnetic forces, dark matter might have its own rich variety of interactions that allow it to form dark atoms, dark molecules, and perhaps even dark planets and dark stars. Gently, we discover that the concept of a dark sector opens up fascinating possibilities for the structure and behavior of dark matter. If dark matter particles can interact with each other through dark electromagnetic forces, they might be able to dissipate energy and collapse into dense structures in ways that would significantly affect galaxy formation and evolution. These self-interacting dark matter models predict subtle differences in the distribution of matter within galaxies that might be detectable through careful astronomical observations. In the quiet space of theoretical contemplation, we also encounter the possibility that our understanding of gravity itself might need modification rather than requiring the existence of invisible matter. These alternative theories, known collectively as modified Newtonian dynamics or MOND, suggest that the laws of gravity might behave differently on very large scales, or in regions of extremely weak gravitational fields. Let us drift into an appreciation of how MOND theories attempt to explain the same observations that led to the dark matter hypothesis, by proposing that gravitational attraction becomes stronger than expected when accelerations are very small. MOND can account for the flat rotation curves of galaxies without requiring any invisible matter. These theories represent a fundamentally different approach to understanding cosmic structure, one that modifies our understanding of space and time rather than postulating new forms of matter. As our journey continues deeper into theoretical possibilities, we encounter even more exotic candidates for dark matter. Primordial black holes, formed in the extremely early universe from density fluctuations, could potentially account for some or all of the missing mass. These black holes would be completely invisible except for their gravitational effects, making them natural dark matter candidates. Gently, we discover that primordial black holes could exist across an enormous range of masses, from microscopic objects lighter than asteroids to massive black holes, comparable to those found at the centers of galaxies. Different mass ranges for primordial black holes are constrained by different types of observations, creating a complex theoretical landscape that researchers continue to explore. In the quiet space of cosmic contemplation, we also encounter the possibility that dark matter might consist of topological defects in the fabric of space-time itself. These exotic objects, including cosmic strings, domain walls, and monopoles, would arise naturally during phase transitions in the early universe, when the fundamental forces of nature separated from their unified high-energy state. Like whispers in the night, these topological defects would carry tremendous amounts of mass energy while remaining essentially invisible to electromagnetic radiation. They would interact with ordinary matter only through their gravitational fields, making them viable candidates for at least some components of dark matter. The study of topological defects connects dark matter research to some of the most fundamental questions in theoretical physics about the nature of space, time, and the forces that govern the universe. Now we float toward consideration of how these various theoretical possibilities might be distinguished from one another through observation and experiment. Each dark matter candidate makes slightly different predictions about how invisible matter should behave in different cosmic environments, creating opportunities for observational tests that could rule out some possibilities while providing support for others. As our journey continues through this peaceful exploration of theoretical frameworks, we begin to appreciate the profound creativity that theoretical physicists bring to the dark matter problem. Faced with the challenge of explaining observations that clearly indicate the presence of invisible matter, theorists have drawn upon the deepest principles of quantum mechanics, relativity, and thermodynamics to propose solutions that often transcend our everyday intuitions about the nature of reality. Gently, we discover that the theoretical exploration of dark matter has led to significant advances in our understanding of particle physics, cosmology, and even the mathematical structure of physical theories themselves. The search for dark matter has motivated the development of new computational techniques, new mathematical tools, and new ways of thinking about how the universe works on its most fundamental level. In the quiet space of scientific contemplation, we recognize that these theoretical frameworks represent humanity's attempt to understand phenomena that exist far beyond the reach of our direct sensory experience. Through the power of mathematical reasoning and physical intuition, scientists have been able to propose concrete, testable ideas about the nature of invisible matter that comprises the majority of our universe. Let us drift into appreciation of how theoretical dark matter research demonstrates the profound unity of physics across vastly different scales. The same quantum mechanical principles that govern the behavior of subatomic particles also determine the properties of dark matter candidates that shape the evolution of entire galaxies. The mathematical laws that describe particle interactions in laboratory accelerators also govern cosmic processes that created the dark matter we observe throughout the universe. As our contemplative journey prepares to move forward into new realms of exploration, we carry with us a deep appreciation for the theoretical physicists whose creative thinking has opened up so many fascinating possibilities for understanding dark matter. Their work reminds us that science is not just about collecting data and making observations, but also about using human imagination and mathematical reasoning to explore possibilities that extend far beyond what we can directly perceive. In the gentle flow of scientific progress, we see how theoretical and experimental research work together to advance our understanding of cosmic mysteries. Theorists propose new ideas about what dark matter might be. Experimentalists design ingenious ways to test these ideas, and observers search for the subtle signatures that different dark matter candidates would leave in astronomical data. This collaborative process represents science at its most beautiful and most effective. Like whispers in the night, these theoretical frameworks remind us that the universe may be far stranger and more wonderful than we currently imagine. Each proposed dark matter candidate opens up new possibilities for understanding the fundamental nature of reality, new connections between seemingly unrelated areas of physics, and new questions that will inspire future generations of researchers to probe ever deeper into the cosmic mysteries that surround us all. Now we float toward contemplation of how dark matter serves as the invisible architect of cosmic structure, shaping the universe's grandest features through the gentle but persistent influence of gravity. In the quiet space of cosmic evolution, dark matter has guided the formation of galaxies, sculpted the cosmic web that connects all matter across vast distances, and created the gravitational scaffolding upon which the visible universe has been built over billions of years of cosmic history. As our journey continues into this realm of cosmic architecture, we encounter the profound realization that dark matter began shaping the universe long before the first stars ignited or the first galaxies assembled. In the earliest epochs following the Big Bang, when the universe was still a hot, dense plasma of elementary particles, dark matter was already beginning to clump together under its own gravitational attraction, creating the seeds that would eventually grow into the massive structures we observe today. Gently, we discover that dark matter's head start in structure formation was crucial for the development of cosmic complexity. Because dark matter does not interact electromagnetically, it was not affected by the radiation pressure that kept ordinary matter in a smooth, hot plasma for hundreds of thousands of years after the Big Bang. While ordinary matter remained uniform and featureless, dark matter was free to begin the patient process of gravitational collapse that would eventually create the universe's hierarchical structure. In the quiet space of cosmic evolution, computer simulations reveal the beautiful process by which dark matter transforms from nearly uniform density fluctuations into the complex cosmic web we observe today. These computational models, running on some of the world's most powerful supercomputers, follow billions of dark matter particles as they interact gravitationally over cosmic time, creating a detailed picture of how invisible matter organizes itself into the universe's largest structures. Like whispers in the night, these simulations show how dark matter first forms small clumps that gradually merge and grow through cosmic time. Smaller structures combine to form larger ones in a hierarchical process that astronomers call bottom-up structure formation. This elegant process creates a universe filled with dark matter halos of all sizes, from tiny subgalactic clumps to massive galaxy clusters, containing thousands of individual galaxies. Let's drift into contemplation of how galaxies form within this dark matter framework. The luminous matter that we observe in galaxies, the stars, gas, and dust that emit electromagnetic radiation, represents only a small fraction of each galaxy's total mass. The majority of galactic matter exists as an invisible dark matter halo that extends far beyond the visible galactic disk and provides the gravitational environment necessary for galaxy formation and evolution. As our journey continues through this peaceful exploration of cosmic architecture, we begin to appreciate how dark matter halos serve as the cosmic nurseries where galaxies are born and raised. The gravitational potential wells created by dark matter concentrations provide the framework within which ordinary matter can collect, cool, and eventually form the stars that make galaxies visible to our telescopes. Gently, we discover that the properties of dark matter halos, their masses, their density profiles, their shapes directly influence the characteristics of the galaxies they host. Massive dark matter halos tend to host large elliptical galaxies, while smaller halos are associated with spiral galaxies like our own Milky Way. The relationship between dark matter halos and their galactic contents represents one of the most active areas of current astrophysical research. In the quiet space of galactic dynamics, dark matter continues to play a crucial role throughout a galaxy's lifetime. The dark matter halo provides the gravitational stability that allows spiral galaxies to maintain their elegant structure over billions of years. Without this invisible framework, the differential rotation of galactic disks would quickly destroy the spiral patterns that make these galaxies so beautiful in astronomical images. Now we float toward understanding how dark matter shapes structure on even larger scales. Through the formation of the cosmic web, this vast network of filaments, nodes, and voids represents the largest scale structure in the universe. A delicate tracery that spans billions of light years and connects all matter in an intricate, cosmic tapestry. Like whispers in the night, the cosmic web reveals itself through the distribution of galaxies across the sky, but its underlying structure is determined primarily by the invisible distribution of dark matter. The filaments of the cosmic web mark the locations where dark matter has been drawn together by gravity, creating highways along which ordinary matter flows to feed the growth of galaxies and galaxy clusters. As our journey continues deeper into this contemplation of cosmic architecture, we encounter the profound beauty of gravitational lensing, a phenomenon that allows astronomers to map the distribution of dark matter directly. When light from distant galaxies passes near massive concentrations of dark matter, the curvature of space-time bends the light rays, creating distorted or multiple images of the background galaxies. Gently, we discover that gravitational lensing serves as nature's own telescope, allowing us to observe dark matter's gravitational effects with exquisite precision. Strong gravitational lensing, which occurs near the most massive galaxy clusters, can create spectacular Einstein rings and arc-like images that provide detailed information about how dark matter is distributed within these cosmic giants. In the quiet space of observational astronomy, gravitational lensing offers an even more powerful tool for mapping dark matter across vast cosmic distances. By measuring the subtle distortions that dark matter concentrations produce in the shapes of millions of background galaxies, astronomers can create detailed maps showing how invisible matter is distributed throughout the universe. Let's drift into appreciation of how these dark matter maps reveal the universe's hidden architecture. They show a cosmos dominated by vast, nearly empty voids separated by dense filaments and nodes where matter has collected. Under gravity's patient influence, this structure bears little resemblance to the random distribution we might expect if matter were scattered uniformly, instead revealing the complex patterns that emerge when gravity has billions of years to organize matter on cosmic scales. As our journey continues through this peaceful exploration, we encounter the role that dark matter plays in galaxy cluster formation. These massive structures, containing hundreds or thousands of individual galaxies, represent the largest gravitationally bound objects in the universe. They serve as cosmic laboratories where the effects of dark matter can be studied in detail through multiple independent techniques. Gently, we discover that galaxy clusters provide some of the most compelling evidence for dark matter's existence. The motions of individual galaxies within clusters indicate the presence of far more matter than can be accounted for by visible stars and gas. X-ray observations reveal hot intracluster gas that requires massive dark matter halos to remain gravitationally bound. Gravitational lensing measurements directly map the distribution of invisible matter within these cosmic structures. In the quiet space of cluster dynamics, we observe how dark matter provides the gravitational scaffolding that holds these massive structures together over cosmic time. Without dark matter's invisible embrace, galaxy clusters would have dispersed long ago, their constituent galaxies scattered into the cosmic void by their own orbital motions. Now we float toward understanding how dark matter influences the formation and evolution of individual galaxies through processes such as galaxy mergers and interactions. When two galaxies approach each other, their dark matter halos begin to interact gravitationally long, before the visible components of the galaxies show any signs of disturbance. Like whispers in the night, these dark matter interactions can significantly affect galactic evolution. They can trigger bursts of star formation, distort galactic shapes, and eventually lead to complete galactic mergers that create new, larger systems. The Milky Way's own history has been shaped by such interactions, including the ongoing merger with the Sagittarius dwarf galaxy and the anticipated collision with the Andromeda galaxy in several billion years. As our journey continues through this contemplative exploration of cosmic architecture, we begin to appreciate how dark matter creates a universe that is both stable and dynamic. The invisible scaffolding of dark matter provides the long-term stability necessary for complex structures to form and persist, while also allowing for the ongoing evolution and growth that keeps the cosmos interesting and dynamic. Gently, we discover that dark matter's role in cosmic architecture extends beyond simply providing gravitat, ional attraction. The way that dark matter is distributed, its density profiles, its substructure, its response to tidal forces affects virtually every aspect of how galaxies form, evolve, and interact with their cosmic environment. In the quiet space of current research, astronomers are working to understand how dark matter properties might vary from place to place in the universe. Do all dark matter halos have similar internal structures? Or do they vary in ways that depend on their formation history or local environment? How do dark matter substructures within larger halos affect the galaxies they contain? These questions represent the frontier of current dark matter research. Let's drift into contemplation of how dark matter architecture influences the cosmic conditions necessary for life. The gravitational scaffolding provided by dark matter determines where galaxies form, how they evolve, and what kinds of stellar populations they contain. All of these factors ultimately influence the distribution of heavy elements necessary for rocky planets and the long-term stability of planetary systems, where life might develop. As our peaceful journey prepares to move forward into new realms of exploration, we carry with us a profound appreciation for dark matter's role as the universe's invisible architect. Through the patient, persistent influence of gravity, dark matter has shaped every aspect of cosmic structure from the largest galaxy clusters to the smallest galactic satellites, creating a universe rich in complexity and beauty. In the gentle flow of cosmic evolution, we see how dark matter represents far more than just a missing mass problem to be solved. It is the fundamental framework upon which all cosmic complexity has been built, the invisible foundation that makes possible the rich tapestry of structure we observe throughout the universe. Without dark matter's architectural influence, the cosmos would be a far simpler, far less interesting place, a universe without galaxies, without stars, and without the conditions necessary for life itself. As our journey continues deeper into the cosmic mystery, we now float toward the realm of modern experimental searches for dark matter, where scientists around the world have created some of the most sensitive instruments ever conceived to listen for the whispers of invisible particles. In the quiet space of underground laboratories, particle accelerators, and space-based observatories, researchers conduct a patient vigil, waiting for the subtle signals that might finally reveal the true nature of the universe's most abundant form of matter. Let us drift into the serene underground sanctuaries, where direct detection experiments wait in perfect silence for dark matter particles to reveal themselves. These laboratories buried deep beneath the Earth's surface in locations like the Sanford Underground Research Facility in South Dakota, the Gran Sasso National Laboratory in Italy, and the Snow Lab facility in Canada provide the ultimate quiet environment for conducting the most sensitive measurements in the history of science. Gently, we discover that these underground locations are chosen specifically to shield the delicate detectee on equipment from the constant shower of cosmic rays that bombards the Earth's surface. By placing their experiments under thousands of feet of rock, scientists create cosmic quiet zones where the only remaining particles that can penetrate to the detector level are neutrinos and, potentially, dark matter particles themselves. In the quiet space of these underground cathedrals of science, researchers have constructed detectors of extraordinary sensitivity. Some experiments use ultra-pure crystals of silicon or germanium, cooled to temperatures just above absolute zero, that would register the tiny amount of heat deposited if a dark matter particle were to collide with an atomic nucleus. Other experiments use tanks of liquid xenon, carefully purified to remove all traces of radioactive contamination, that would produce flashes of light when dark matter particles interact with xenon atoms. Like whispers in the night, these direct detection experiments are listening for signals so subtle that they might occur only a few times per year in detector masses measured in tons. The challenge is extraordinary. Scientists must distinguish genuine dark matter interactions from the unavoidable background of radioactive decays, cosmic ray muons, and even vibrations from distant earthquakes or passing trucks on the surface above. As our journey continues through this peaceful exploration of experimental techniques, we encounter the remarkable engineering achievements that make these searches possible. The most sensitive dark matter detectors are marvels of technology, featuring ultra-low background materials, sophisticated shielding systems, and electronics capable of measuring energy depositions smaller than the binding energy of a single chemical bond. Gently, we discover that the quest for ever lower background levels has driven innovations in materials, science, electronics, and detector technology that benefit many other areas of scientific research. The techniques developed for dark matter detection have applications in nuclear physics, medical imaging, and even national security, demonstrating how fundamental research often leads to unexpected practical benefits. Now we float toward the complementary approach of indirect detection, where scientists search for the products of dark matter particle annihilation or decay rather than trying to observe dark matter particles directly. These experiments look for excess gamma rays, antimatter particles, or neutrinos that would be produced if dark matter particles occasionally interact with each other and convert their mass into more familiar forms of matter and energy. In the quiet space of gamma-ray astronomy, space-based telescopes, like the Fermi Gamma-Ray Space Telescope, conduct systematic surveys of the sky, searching for the telltale signatures of dark matter annihilation in regions where invisible matter is known to be concentrated. The centers of galaxies, the hearts of galaxy clusters, and the remnants of small galaxies that have been torn apart by tidal forces, all represent potential sources of dark matter signals. Like whispers in the night, these indirect signals would appear as subtle excesses in the flux of high-energy particles, coming from directions where dark matter concentrations are expected to be highest. The challenge lies in distinguishing genuine dark matter signals from the many astrophysical processes that can also produce gamma rays, antimatter, and neutrinos through more conventional mechanisms. Let us drift into contemplation of the balloon-borne and space-based experiments that search for antimatter particles that might be produced by dark matter annihilation. Experiments like the alpha magnetic spectrometer aboard the International Space Station measure the flux of cosmic ray antiprotons and positrons with unprecedented precision, looking for the subtle signatures that would indicate a dark matter origin for some of these exotic particles. As our journey continues deeper into this realm of experimental searches, we encounter the third major approach to dark matter detection, collider searches, that attempt to create dark matter particles in high-energy particle accelerators. The Large Hadron Collider at CERN, the world's most powerful particle accelerator, regularly creates conditions of energy and density that haven't existed in the universe since the first moments after the Big Bang. Gently, we discover that collider searches for dark matter involve looking for missing energy signatures in particle collision events. If dark matter particles were created in these high-energy collisions, they would immediately escape the detector without leaving any direct trace, but their presence could be inferred from the apparent non-conservation of energy and momentum in the observed collision products. In the quiet space of particle physics laboratories, these collider searches provide crucial complementary information to direct and indirect detection experiments, while underground detectors probe dark matter interactions at very low energies. Collider experiments can explore higher energy regimes, where different dark matter production mechanisms might become important. Now we float toward the space-based observatories that are revolutionizing our understanding of dark matter through precision cosmological measurements. Missions like the recently launched Euclid Telescope and the upcoming Nancy Grace Roman Space Telescope are designed to map the distribution of dark matter across cosmic distances with unprecedented accuracy and detail. Like whispers in the night, these space-based surveys reveal dark matter's presence through its gravitational effects on the large-scale structure of the universe. By measuring the positions and shapes of billions of galaxies across vast cosmic volumes, these missions can create detailed three-dimensional maps, showing how dark matter is distributed throughout space and how this distribution has evolved over cosmic time. As our journey continues through this peaceful exploration of modern searches, we encounter the remarkable precision that these cosmological surveys have achieved. The Planck mission's measurements of the cosmic microwave background radiation have determined dark matter's abundance in the universe to better than 1% accuracy, providing crucial constraints on theoretical models of what dark matter might be. Gently, we discover that these precise cosmological measurements create a beautiful synergy with laboratory searches for dark matter particles. The astronomical observations tell us how much dark matter exists and how it behaves on cosmic scales, while the laboratory experiments probe the microscopic properties of individual dark matter particles. Together, these approaches provide complementary pieces of the cosmic puzzle. In the quiet space of international collaboration, dark matter research has become a truly global enterprise involving thousands of scientists from dozens of countries. Major experiments like the Lux Zeppelin detector in South Dakota, the Xenon experiment in Italy, and the Darwin project being planned for Europe represent collaborative efforts that pull the expertise and resources of the worldwide scientific community. Let's drift into appreciation of how these collaborative efforts exemplify science at its best. Researchers from different countries, institutions, and backgrounds work together toward the common goal of understanding one of the universe's greatest mysteries. They share data, techniques, and insights in a spirit of open scientific inquiry that transcends national boundaries and cultural differences. As our journey continues deeper into this contemplation of modern searches, we begin to appreciate the remarkable sensitivity that current experiments have achieved. The most advanced direct detection experiments can observe dark matter interaction rates as low as 1 event per ton of detector material per year, requiring years of patient data collection to accumulate sufficient statistics for meaningful scientific conclusions. Gently, we discover that this extraordinary sensitivity comes at the cost of requiring extremely careful control of all possible sources of background signals. Scientists must account for radioactive contamination at the level of parts per trillion, shield their detectors from cosmic rays and environmental radiation, and operate their experiments in the most stable, quiet environments on Earth. Now we float toward consideration of the future generation of dark matter searches that are currently being planned and constructed. These next-generation experiments will be even larger, more sensitive, and more sophisticated than current detectors, pushing the boundaries of what is technologically possible. In the quest to detect dark matter particles directly, in the quiet space of experimental planning, scientists are designing detectors with masses measured in tens of tons, rather than hundreds of kilograms. Underground facilities, located even deeper beneath the Earth's surface, and shielding systems that will reduce background signals to levels never before achieved. These future experiments represent humanity's most ambitious attempt yet to solve the dark matter mystery through direct particle detection. Like whispers in the night, These advanced experiments will probe theoretical parameter space that has never been accessible to previous searches. They will be sensitive to dark matter interaction rates that are predicted by many theoretical models, potentially providing the first direct evidence for dark matter particles that has eluded scientists for decades. As our peaceful journey through the realm of modern searches begins to draw toward its close, we carry with us a profound appreciation for the ingenuity, patience, and dedication of the researchers who have devoted their careers to this cosmic quest. Their work represents the scientific method at its most rigorous and most inspiring, demonstrating humanity's capacity to probe the deepest mysteries of existence through careful observation, creative experimentation, and persistent investigation. In the gentle flow of scientific progress, we see how each new generation of experiments builds upon the achievements of previous efforts, gradually pushing toward ever greater sensitivity and more comprehensive coverage of theoretical possibilities, whether dark matter reveals itself through direct detection, indirect signatures, collider production, or astronomical observations. The worldwide community of researchers stands ready to recognize and understand these cosmic whispers when they finally make themselves known. As our journey continues floating through the cosmic ocean of understanding, we now drift toward one of the most profound and contemplative questions in all of science. How does dark matter influence the conditions necessary for life throughout the universe? In the quiet space where cosmology meets astrobiology, we discover that the invisible scaffolding of dark matter has played a crucial though subtle role in creating the cosmic environments where life might emerge, evolve, and flourish across billions of years of cosmic history. Gently, we discover that dark matter's influence on life begins at the very largest scales of cosmic structure. The gravitational architecture created by dark matter determines where galaxies form, how they evolve, and what kinds of stellar populations they contain. All of these factors ultimately affect the production and distribution of the heavy elements carbon, oxygen, nitrogen, phosphorus, and others that appear to be essential ingredients for life as we understand it. In the quiet space of galactic evolution, dark matter halos provide the stable gravitational environments necessary for galaxies to maintain active star formation over billions of years. Without this invisible scaffolding, galaxies would be unable to retain the gas supplies needed for continued stellar birth, and the production of life-supporting elements would cease prematurely. The patient, persistent influence of dark matter ensures that galaxies can continue creating heavy elements throughout cosmic time. Let us drift into contemplation of how dark matter influences the concept of galactic habitable zones, regions within galaxies where conditions might be most favorable for the development of life. Just as individual stars have habitable zones where liquid water can exist on planetary surfaces, galaxies appear to have regions where the conditions for life are optimized over cosmic timescales. Like whispers in the night, dark matter helps determine these galactic habitable zones through its influence on stellar populations, supernova rates, and the distribution of heavy elements throughout galactic disks. Regions close to galactic centers may experience frequent disruptions from supermassive black holes and high rates of stellar explosions, while regions far from galactic centers may lack sufficient heavy elements for rocky planet formation. As our journey continues through this peaceful exploration of cosmic habitability, we encounter the realization that dark matter's role in galaxy formation has directly influenced the timeline of cosmic evolution that made complex life possible. The hierarchical assembly of dark matter structures determined when the first galaxies formed, when they began producing heavy elements in significant quantities, and when conditions became suitable for the formation of planetary systems capable of supporting life. Gently, we discover that the universe's expansion rate, partially determined by dark matter's gravitational influence, has created a cosmic timeline that appears remarkably well suited for the development of complexity. If dark matter were significantly more or less abundant, the universe might have evolved too quickly for stable structures to form, or too slowly for sufficient heavy element production to occur within reasonable cosmic timescales. Now we float toward understanding how dark matter influences star formation processes that are crucial for creating the kinds of stellar environments where habitable planets might exist. The density and structure of dark matter halos affect how gas flows into galaxies, how it cools and condenses to form stars, and what kinds of stellar masses are preferentially produced in different galactic environments. In the quiet space of stellar nurseries, dark matter's gravitational influence helps create the conditions where long-lived, stable stars like our Sun can form and maintain steady energy output for billions of years. The mass function of newly formed stars, the relative numbers of high-mass and low-mass stars that are born in each stellar generation, is influenced by the dark matter environment in ways that affect both heavy element production and the likelihood of forming planetary systems suitable for life. Like whispers in the night, dark matter's influence extends to the formation and evolution of individual planetary systems. Through its effects on the dynamics of protoplanetary disks and the migration of forming planets, computer simulations suggest that the gravitational environment provided by dark matter halos can influence how planetary systems assemble, potentially affecting the likelihood of forming terrestrial planets in habitable zones around their host stars. Let us drift into contemplation of how dark matter might influence the long-term stability of planetary orbits over billions of years of evolution. The invisible matter that permeates our galaxy creates a smooth gravitational background that helps stabilize the orbits of stars like our Sun as they journey around the galactic center. This stability is crucial for maintaining the kinds of long-term environmental conditions that appear necessary for the evolution of complex life. As our journey continues deeper into this astrobiological contemplation, we encounter the fascinating possibility that dark matter streams passing through our solar system might have subtle effects on planetary climates and evolution. While these effects would be extraordinarily small, some researchers have speculated about whether variations in local dark matter density might influence long-term climate patterns, or even biological evolution through their effects on planetary dynamics. Gently, we discover that the search for dark matter has led to the development of detection techniques and technologies that also have applications in astrobiology research. The ultra-sensitive instruments designed to detect dark matter particles are providing new tools for studying the composition of planetary atmospheres, the mineralogy of meteorites, and the organic chemistry of interstellar space. In the quiet space of interdisciplinary research, we find that dark matter studies and astrobiology investigations share many common themes and approaches. Both fields require understanding how cosmic scale processes influence smaller scale phenomena. Both involve searching for extremely subtle signals in complex data sets, and both push the boundaries of what is technologically possible in terms of sensitive measurements and sophisticated theoretical modeling. Now we float toward consideration of how dark matter research might inform our search for life beyond Earth. Understanding the distribution of dark matter throughout our galaxy and beyond helps astrobiologists identify the regions where conditions for life might be most favorable, guiding future searches for habitable exoplanets and potential biosignatures in their atmospheres. Like whispers in the night, dark matter maps created by gravitational lensing surveys and other astronomical techniques provide valuable information about the large-scale structure of our cosmic neighborhood. These maps help identify which stellar regions have the most stable gravitational environments, the richest concentrations of heavy elements, and the longest histories of steady star formation, or factors that might influence the likelihood of finding life. As our journey continues through this contemplative exploration, we begin to appreciate how dark matter research has contributed to our understanding of the cosmic context within which life on Earth has evolved. The realization that we live in a universe dominated by invisible matter has profound implications for how we think about our place in the cosmos and the likelihood of finding life elsewhere in the universe. Gently, we discover that dark matter's role in cosmic evolution suggests that life, if it exists elsewhere, has likely been influenced by the same invisible forces that have shaped our own galactic environment. The universal nature of dark matter means that biological evolution throughout the cosmos has occurred within the same kind of invisible gravitational scaffolding that has influenced life's development on Earth. In the quiet space of cosmic perspective, we recognize that dark matter connects astrobiology to some of the deepest questions in fundamental physics. Understanding what dark matter is and how it behaves could provide crucial insights into the physical laws that govern the universe, laws that ultimately determine what kinds of complexity and organization are possible in cosmic environments. Let's drift into contemplation of how future dark matter discoveries might influence astrobiology research. If dark matter turns out to consist of particles that interact with ordinary matter in previously unknown ways, these interactions might have subtle but detectable effects on biological systems, planetary atmospheres, or the chemistry of life-supporting environments. As our journey continues deeper into this intersection of cosmology and biology, we encounter the possibility that dark matter physics might provide new tools for life detection. Some theoretical models suggest that dark matter interactions could produce unique signatures in planetary atmospheres or biological systems that might serve as novel biosignatures detectable by future space-based observatories. Gently, we discover that the study of dark matter has also influenced our thinking about the concept of habitability itself. The realization that the universe contains forms of matter and energy that transcend our direct experience has encouraged astrobiologists to think more broadly about what kinds of environments might support life and what forms such life might take. Now we float toward understanding how dark matter research contributes to our appreciation of the cosmic conditions that have made Earth's biosphere possible. The invisible matter that shapes galactic structure has influenced every aspect of our planet's cosmic environment, from the heavy element composition of the solar nebula, from which Earth formed, to the long-term stability of our solar system's orbit around the galactic center. In the quiet space of this realization, we begin to see how dark matter represents more than just a scientific puzzle to be solved. It is a fundamental component of the cosmic ecosystem, within which all life, including human life, has evolved. Understanding dark matter helps us understand the deep cosmic roots of our own existence and the cosmic processes that continue to influence life on Earth today. Like whispers in the night, the connection between dark matter and astrobiology reminds us that life exists within a vast, complex, and largely invisible cosmic context. Every living organism on Earth, from the smallest microbe to the largest whale, has been shaped by evolutionary processes that occurred within a universe dominated by dark matter's gravitational influence. As our contemplative journey through this astrobiological connection begins to draw toward its close, we carry with us a profound appreciation for the deep connections between cosmic-scale physics and the biological processes that have given rise to life, intelligence, and consciousness in our universe. The invisible matter that shapes cosmic structure has also, in subtle but crucial ways, shaped the evolutionary path that led to our own existence and our capacity to contemplate these cosmic mysteries. As our journey continues floating through the vast cosmic ocean of understanding, we now drift toward the deeper philosophical questions that dark matter poses about the nature of reality, knowledge, and humanity's place in an invisible universe. In the quiet space of contemplation, we find that dark matter challenges not only our scientific theories, but also our most fundamental assumptions about what exists, what can be known, and what it means to be conscious beings in a cosmos dominated by the unseen. Gently, we discover that dark matter represents one of the most profound epistemological challenges in the history of human thought. For millennia, human understanding of the natural world has been built upon the foundation of sensory experience. What we can see, touch, hear, smell, and taste. Dark matter forces us to acknowledge that the vast majority of cosmic reality lies completely beyond the reach of our direct sensory experience, accessible only through the abstract language of mathematics and the indirect inferences of scientific reasoning. In the quiet space of philosophical reflection, we encounter the humbling realization that dark matter reveals the fundamental limitations of human perception. Our evolved sensory systems, magnificent as they are for navigating the terrestrial environment where our species developed, provide us with access to only a tiny fraction of what actually exists in the universe. The invisible ocean of dark matter that surrounds us serves as a constant reminder of how much reality transcends our direct awareness. Like whispers in the night, dark matter speaks to us about the provisional nature of all human knowledge. Every generation of scientists has believed that their understanding of the universe was essentially complete, only to have subsequent discoveries reveal vast realms of previously unknown phenomena. Dark matter represents perhaps the most dramatic example of this pattern, showing us that even our most sophisticated theories account for only a small portion of cosmic reality. Let us drift into contemplation of what dark matter teaches us about the relationship between the seen and the unseen in human experience. Throughout history, humans have intuited that reality extends beyond what is immediately apparent to the senses. Religious traditions speak of spiritual realms, philosophers contemplate abstract universals, and artists attempt to capture ineffable truths that transcend literal representation. Dark matter provides a scientific parallel to these ancient intuitions about hidden dimensions of existence. As our journey continues through this peaceful philosophical exploration, we encounter the profound questions that dark matter raises about the nature of scientific knowledge itself. How can we claim to understand a universe that is dominated by a form of matter we cannot directly observe? What does it mean to have scientific knowledge of phenomena that exist completely outside our sensory experience? These questions challenge the empirical foundations of scientific methodology, while simultaneously demonstrating the power of human reasoning to transcend the limitations of direct observation. Gently, we discover that dark matter exemplifies both the greatest triumph and the greatest humility of human scientific understanding. It represents a triumph because we have been able to infer its existence and properties through careful observation and mathematical analysis, demonstrating the remarkable power of human intelligence to comprehend aspects of reality that lie far beyond direct experience. Yet it also represents a profound humility, because it reminds us how much we still do not know about the fundamental nature of existence itself. Now we float toward consideration of how dark matter influences our understanding of consciousness and its place in the cosmic order. If the universe is indeed dominated by invisible matter that interacts with ordinary matter only through gravity, what does this tell us about the cosmic significance of consciousness which has emerged from ordinary matter through billions of years of evolution? Are conscious beings like ourselves cosmically insignificant specks in a universe dominated by invisible forces? Or do we represent something uniquely valuable precisely because we are capable of contemplating these hidden cosmic realities? In the quiet space of cosmic perspective, we find that dark matter paradoxically both diminishes and enhances the significance of conscious life. On one hand, the realization that conscious beings are composed of the minority form of cosmic matter might seem to reduce our importance in the grand cosmic scheme. On the other hand, the fact that consciousness has emerged from ordinary matter and is capable of comprehending the invisible universe suggests that awareness itself might represent a phenomenon of extraordinary cosmic significance. We're drifting gently through the vast cosmic ocean, tracing the quiet wake of our voyage, a journey that has carried us far beyond the boundaries of what our eyes can see into the invisible realms that cradle the universe itself. As we float now toward the end of our exploration, let us look back softly, like stargazers recalling constellations, and remember the path that brought us here. We began at the edge of knowledge in a cosmos woven of light and darkness. Galaxies, stars, and planets spun in silent harmony, but something was missing, something unseen, unaccounted for, and yet profoundly present. It was the invisible thread pulling galaxies into their graceful spirals, the hidden sculptor shaping clusters and filaments into cosmic architecture. It was dark matter, not a substance we could touch or see, but a presence felt everywhere, a gravitational whisper that revealed itself only through the motion of the universe. In the early chapters of our journey, we followed the quiet footsteps of discovery. Astronomers, gazing through their telescopes, began to notice peculiarities. Galaxies spun too quickly at their edges as if held by invisible hands. Stars danced in patterns that defied Newtonian predictions. In the 1930s, Fritz Zwicky measured the speeds of galaxies in the Coma cluster and spoke of Dunkelmaterie, dark matter, as the missing mass holding them together. And decades later, Vera Rubin traced the rotation curves of spiral galaxies and found them inexplicably flat, as if gravity itself were being guided by an unseen companion. There was no thunderous revelation, no triumphant announcement, only a deepening quiet, a gentle realization that the universe we knew was incomplete. What we could see, all the stars, planets, gas, dust, and glowing galaxies, accounted for less than 5% of the cosmos. The rest, dark and silent, remained beyond the reach of our senses. From there, we drifted deeper into the realm of theory. Physicists and cosmologists began to imagine what dark matter might be. Could it be composed of WIMPs, weakly interacting massive particles, drifting invisibly through every cubic centimeter of space? Could it be Axions, born from the early universe, humming faintly in the background of existence? Or perhaps sterile neutrinos, ghostly cousins of known particles, swimming silently through cosmic seas? And beyond particles, other ideas floated into view: modified gravity, hidden dimensions, or entire frameworks yet unimagined. Each theory was a quiet note in the cosmic symphony, each one a soft attempt to explain the universe's missing mass. We explored how this invisible matter sculpts the cosmos. Without dark matter, galaxies might never have formed. Its gravity seeded the first structures in the early universe, drawing gas into filaments and knots that became stars and galaxies. Even now, the great cosmic web, a vast, interconnected lattice of matter stretching across billions of light years, is woven primarily from dark matter-esque gravitational threads. It is the silent architect of the universe's large-scale structure, the hidden hand shaping everything we see. We gazed upon gravitational lensing, the bending of light by massive structures, and marveled at how dark matter, though invisible, leaves imprints in the pathways of photons. We saw galaxy clusters bound in dark embraces, held together by far more mass than their luminous matter could account for. In every corner of the cosmos, dark matter was there, not as a spotlight, but as the unseen stage upon which cosmic drama unfolds. And in the quiet laboratories of Earth, scientists listened for its faintest whispers. Deep underground, shielded from cosmic rays, detectors waited patiently for a single interaction, a fleeting collision that might reveal a WIMP. Particle accelerators, like the Large Hadron Collider, smashed protons together at near light speed, hoping that dark matter might appear among the debris. Space-based telescopes scanned the heavens for subtle gravitational effects or indirect signals. Missions like Euclid and WFIR-ST promised to map the invisible landscape with exquisite precision. All of it, every experiment, every observation, was part of humanity's patient attempt to listen to the cosmos' quietest voice. Even more wondrously, we glimpsed how dark matter might be woven into the story of life itself. It influences star formation, regulates the pace of galactic evolution, and shapes the environments where planets and perhaps life emerge. Habitable zones may owe their stability, in part, to the gravitational scaffolding dark matter provides. It is humbling to imagine that the chemistry of oceans, the warmth of suns, and the possibility of life's emergence might all be gently guided by something we cannot see. And finally, we reflected on what this mystery teaches us about the cosmos and about ourselves. Dark matter reminds us that most of reality is hidden. It teaches humility, that our senses and instruments, remarkable though they are, capture only a fraction of existence. It encourages patience, inviting us to listen deeply and look beyond the obvious. And it inspires wonder, a profound sense of awe that the universe is vaster, subtler, and more mysterious than we can imagine. As we now near the end of our journey, drifting softly on this sea of stars, the mystery remains unsolved. We have measured its influence, mapped its distribution, and constrained its properties, and yet we do not know what dark matter truly is. It remains a cosmic lullaby sung just beyond our hearing, a puzzle that invites us not to frustration but to curiosity. The search itself, slow, careful, and patient, is part of what it means to be human. Our peaceful voyage through the cosmos has shown us not just the universe's hidden scaffolding, but something deeper about ourselves, that we are explorers by nature, dreamers in a dark and boundless ocean, listening for whispers in the silence. And though we may not yet have the answers, the journey itself, this gentle pursuit of knowledge, this cosmic meditation is its own reward. As we drift onward beneath the velvet canopy of the cosmos, we realize that our exploration of dark matter is not a destination but a path, a road, that stretches quietly into the unknown. Every observation, every theory, every experiment is not an endpoint, but a step along a journey that humanity has been on since the first eyes, lifted toward the night sky. And like those early stargazers who sought patterns among the stars, we too are seekers, searching not for answers that end the story, but for questions that deepen it. The search for dark matter is one of the most profound quests in all of science. It is not driven by utility or by immediate reward. Instead, it is powered by curiosity, that quiet, unshakable human urge to understand the universe that gave us birth. It is a search carried out not with trumpets and fanfare, but with patience and humility. Generations of scientists dedicate their lives to listening for a single collision, to decoding faint signals from distant galaxies, to refining equations that describe what might lie beneath reality's surface. And this quest has already changed us. Each discovery, each non-detection, each new insight shapes not just our knowledge of the cosmos, but our sense of who we are within it. The invisible matter that holds galaxies together also holds together our collective endeavor to seek truth. The questions it raises ripple outward, influencing fields from particle physics to cosmology, from philosophy to theology. It forces us to confront the limits of what we know, and to embrace the beauty of what we do not. The ongoing search unfolds on many fronts. Deep beneath mountains and inside old mines, detectors lie waiting in silence, sensitive enough to feel the faintest touch of a passing particle. They may wait for years, even decades, for a single event, and yet they keep listening. It is a testament to the patience and perseverance that science demands. Above the atmosphere, satellites scan the skies for subtle distortions in starlight or for high-energy particles that might hint at dark matter-esque decay. And in the world's most powerful accelerators, particles are smashed together in the hope of glimpsing the unseen. Each of these efforts is like a candle lit against the cosmic dark, tiny, fragile flames that together illuminate the vast unknown. And with each year, those flames grow brighter. The data becomes more precise, the theories more refined, the instruments more sensitive. We may not yet know what dark matter is, but we are closing in, guided not by certainty but by curiosity and care. Beyond the laboratories and observatories, this quest also inspires deeper reflection. It compels us to question our assumptions about the universe itself. If most of the cosmos is made of something we cannot see, cannot touch, cannot even fully describe, then what does that say about reality? Perhaps the universe is not built to be easily understood. Perhaps it is a tapestry woven from both light and shadow, presence and absence. And perhaps the most important truths are not the ones that reveal themselves quickly, but those that wait patiently for us to grow wise enough to perceive them. There is also a humbling symmetry in this search. Just as our ancestors once believed Earth to be the center of the universe, we once believed that the visible cosmos was the whole of existence. But time and discovery have gently corrected our view. We now know that we are adrift in a vast, expanding universe, and that the matter we see is but a sliver of what is truly there. The rest, the dark matter and dark energy, lies beyond the reach of our senses. Yet it shapes everything. It is a quiet reminder that reality is always deeper than it appears, that the surface is only the beginning. This humbling lesson reaches beyond science. It invites us to look at ourselves and one another with the same humility. Just as the cosmos is more than meets the eye, so too are we. Beneath the visible surfaces of our lives, our actions, our words, our appearances, there are hidden depths, emotions, thoughts, hopes, fears. The invisible shapes the visible, in the universe and in the human heart alike. And so the search for dark matter becomes a metaphor for something larger, the pursuit of understanding itself. It teaches us that patience is not wasted, that mystery is not failure, and that the unknown is not a void but a frontier. It teaches us that progress is often slow and subtle, not a single leap, but countless quiet steps. And it teaches us that the universe is not something to be conquered, but something to be listened to, contemplated, and cherished. As we float deeper into these reflections, we begin to see that the quest for dark matter is not just about physics, it is about meaning. It is about humanity's endless desire to connect with the cosmos, to trace our origins back to the first flickers of creation, to understand how everything fits together. It is about standing beneath the night sky and knowing that we are part of something unimaginably vast, and yet still striving to know it intimately. We may never capture dark matter in a detector. We may never name its particles or pin down its properties. But even if we don't, the journey itself will have been worth it, because in searching for what is hidden, we come to understand what is visible more deeply. In chasing the unknown, we learn more about ourselves. And in trying to hear the quietest whispers of the cosmos, we discover that we, too, are part of its song. So, let us continue this journey with patience and with wonder. Let us keep listening to the silence, keep searching the dark, keep asking the questions that have no easy answers. For it is in this search, in this shared human endeavor, that we find not only knowledge, but also meaning. Now, as we drift ever so gently toward the final moments of our journey, let us allow the cosmos to cradle us in its quiet embrace. The stars shimmer softly above, like distant lanterns guiding our way, while the unseen dark matter hums its subtle song beneath the surface of everything. The universe, in all its vastness, reminds us that there is always more to explore, more to wonder about, and more to quietly cherish. Throughout our voyage, we have moved with a gentle rhythm, tracing the invisible threads that shape galaxies, weave cosmic filaments, and sustain the universe itself. We have witnessed the delicate dance of matter and gravity, of seen and unseen, and we have learned that much of reality exists in the silence. This is a universe that whispers rather than shouts, a reality that invites contemplation rather than panic. And in listening, in attuning ourselves to its subtlety, we have experienced a rare kind of peace. Our journey has been both scientific and meditative. We have walked alongside the early discoverers, feeling their curiosity, their patience, their quiet awe. We have floated among the theoretical possibilities, letting WIMPs, Axions, and sterile neutrinos drift like gentle clouds through our imagination. We have seen the cosmic web stretch across billions of light years, holding galaxies in tender gravitational embrace, and we have marveled at the silent beauty of gravitational lensing. Each discovery, each revelation, has been a gentle reminder of the intricate harmony of the universe. Even as we reflect on the vast unknowns that remain, there is serenity in knowing that the search itself is meaningful. To seek understanding without haste, to ponder without anxiety, to wonder without expectation. This is the essence of our cosmic meditation. In the patient silence of the laboratories, in the quiet hum of telescopes and detectors, in the thoughtful calculations of theorists, the universe is speaking softly, offering its mysteries to those who listen. And so, we arrive at the philosophical heart of our journey. Dark matter, though unseen, teaches us a profound lesson that what we cannot immediately perceive can be as real and as influential as what is visible. It reminds us that the most important truths are often hidden, that reality is layered, and that humility and patience are our guides through the vast unknown. By embracing the mystery, by acknowledging the limits of our senses, we cultivate a deeper connection with the cosmos and with ourselves. As we settle into this reflective quiet, let us imagine the stars slowly turning overhead, galaxies spinning with eternal grace, and dark matter weaving the cosmic fabric beneath it all. Let us feel the calm rhythm of the universe, steady and enduring, a lullaby older than time. And as we listen, let our minds soften, our thoughts drift, and our hearts expand to include the beauty and mystery that surrounds us. Remember that the universe is not merely a collection of particles and forces, but a vast, interconnected whole. Each star, each galaxy, each speck of dark matter plays a part in the grand design. And we, too, are part of this design, observers, dreamers, seekers of truth, and participants in the gentle unfolding of cosmic wonder. As our journey draws to a close, take a deep, slow breath. Let the calm of the cosmos fill your being. Know that the universe is vast, mysterious, and infinitely patient. The questions we ask today may be answered tomorrow or centuries from now, but the act of seeking, of listening, and of contemplating is timeless. And finally, as we drift into the gentle quiet of night, let us bid farewell, not with haste, but with a soft, peaceful acknowledgement of the cosmos' eternal presence. For in the silence, in the unseen, and in the infinite expanse of space, we find companionship, wonder, and serenity. Good night from the sleepy scientist.